Today we'll design an antenna for 5 gigahertz. So the frequency is 5 gigahertz. You can make a note of it. So for 5 gigahertz, I mentioned 2. Here I mentioned 2, but it's okay. We are going to see only an example. For example, I will take this substrate FR4. So 5 gigahertz for FR4. These are the values: dielectric constant, loss tangent, and thickness. So I will open a document, Word document, and I will start typing the values that I prefer. First thing, can you see the screen?
Yes, sir, we can see, sir.
Frequency is 5 gigahertz. FR4 is my material. So this is going to be my reference document. Whenever you design an antenna, you make a document like this. So you can clearly mention everything. Frequency, F is equal to 5 gigahertz. And type of substrate, FR4. So according to the substrate type, we have other values. They are, you see, dielectric constant. I will, from table, dielectric constant, I have to choose between 4.2 and 4.8. Let us take it as 4.6. I will give the title like micro strip patch antenna. I may save this document. I can save it anywhere I want to. Such documentation will help you. Micro strip patch antenna, I can make it like 5 gigahertz. Okay, I'm going to save it in the desktop of my computer. This is for my reference. So frequency is 5 gigahertz, type of substrate is FR4. From table, dielectric constant is 4.6, and loss tangent. This is one of the important parameters. Loss tangent. How much is it going to be? 0.02 to 0.03. It will be 0.02. Thickness in mm. This is 0.8 to 1.6. It is my choice. I will take 1.6. The thickness is also called height. So called height of substrate. Okay, that is 1.6. So next I will go to RF website. I hope you can understand this. First, I was just selected the frequency value, and then I have chosen type of substrate. Based on the type of substrate from the table, these are the values taken. Okay, and then after taking these values, see frequency is also there. After taking all these values, I am going to everything RF website. Everything RF under everything RF. So in this, I will go under RF calculator strip. RF calculator. Let us click and then go to antenna calculators. And then where do I go? These many types of antennas are available. When you change the type of antenna in CST over here, I'll show you. Just have a look at this so that you can practice. Next, you can see different types of antennas are available. So based on that, you can choose here. Okay. Now we are going with microstrip patch antenna calculator. Click this, and then here they are. These three values should be entered. The dielectric constant value should be entered from here. You see, dielectric constant, it is 4.6. 4.6. And then dielectric height. See, height is 1.6. Okay, height of substrate, or you can mention here itself dielectric. Okay, height of substrate or dielectric, it is 1.6 mm. Already it is here mm. Okay, 1.6. The frequency of operation is how much? 5 gigahertz. So these three values, third, these three values have been entered in this website, 5 gigahertz. So when I hit calculate, the values here. The width is 17.92. The values of epsilon r dielectric height frequency from above. Okay, then we get what we get. We get two different width representations. This is the value in meter, and this is value in millimeter. We choose millimeter references. The width is 17.92. W is equal to 17.92. Please understand it is in mm. Okay, I will not mention, but you please understand it is mm. And then length. Length is equal to 13.46. Now we have calculated these values. Okay, please remember that width is always entered in x-axis values and length is entered in y-axis values. I'll tell you what. So while designing, we use x-axis representation for defining, I mean, for selecting width, and y for length. I'll show you how. So now we have these two values. These calculated values are for, these values are, what are these? Patch values, okay, or dimensions. These are the dimensions of patch. What is a patch? It's here. Look at this. Dimension we have chosen, I mean, we have calculated length and width of patch. The length of patch is 13.46 mm, or you can mention here itself. Width of patch is 17.9. I hope you understand so far. Do you have any doubt until now?
No, sir.
Good. Now what did we do? I will repeat. We have chosen the frequency value. We have according to that, this is chosen according to our requirement, our application, and type of substrate also selected by us. Okay, I will mention as user choice. Okay, so only we can select the values until now. I mean, until selecting the type of substrate. After, we have to follow the procedure. Okay, after selecting the substrate and frequency level, using the table, we have taken these values. Though we didn't use loss tangent, we have to mention it here for reference. So by using these highlighted values in the Everything RF website, under this menu, you can go and calculate. What did we do? We have calculated width and length of the patch. Okay, these are the dimensions of patch we have done so far. After this, we may launch CST Studio Suite, and I will type it here. Launch CST Studio Suite software, and then click new template. I click new template. Wait for a while. In this compass, I will select microwaves and RF optical. Select microwave / RF optical. Okay. Okay, I have selected. Under this, I choose antennas. Okay, after choosing, I click next. Under this, I prefer planar. You can see patch antenna. So planar. Planar, patch, etc. So I have selected this and then click next. I prefer time domain analysis. Okay, I prefer time domain analysis. I'll just leave the values as such because these are all the unit representations. Dimensions are mentioned in millimeter. Frequency is represented in gigahertz. Time, nanoseconds. Temperature is. So these are basic units. So you don't have to disturb it. Let it be. Frequency. Minimum and maximum frequency. the frequency that we are dealing with is 5 gigahertz. So I want to see my antenna's performance over a frequency, over a range of frequencies. There is bandwidth. So I would prefer my antenna to be seen between two different frequencies. For example, my antenna's frequency is 5 gigahertz. So I want to see its performance from 1 gigahertz to 10 gigahertz, or 1 to 15, whatever, or 4 to 15, or 4 to 10. I mean to say a value less than my antenna frequency. Let it be 2 gigahertz, because my antenna's frequency is 5 gigahertz. So I've taken a minimum value as 2, which is less than actual antenna frequency, and maximum value can be 15 or 10, which is higher than my antenna's frequency. My antenna frequency is 5 gigahertz. So I will take 10. You can select 15 also. So over these frequency ranges, the antenna's performance will be displayed. At the end of the simulation, you will be able to see the performance of the antenna between these two frequencies. If I mention 1 and 5, then I may not be able to see my antenna's performance above 5 gigahertz. So it's better to have values like this. Okay. Choose min, max, frequency ranges. I hope it's clear until now. After this, see E field, H field, far field, power flow, power loss. These are all the frequency, parameters, so which we would like to see. At the end of simulation, if I want to see the electric field characteristics, then I should choose it here itself. Okay. But since we are getting started, I will not disturb this. I will leave it as such. Okay. I will click next. So this is the summary of my settings. Finish. I finish. I will be able to see a 3D representation of a template. The template, I hope you can see my cursor. So I can just move it the way I want to. If I want to have a proper view, then I go here, select view. These are the values. See, these numbers are the keyboard number values. If I press number 5, then I will get front view. See, now I'm going to press 5, the front view, the other view. So whatever view I want, generally I prefer number 5. Okay. Based on this perspective, we can change it, right? So I just pressed 5. Now I'm going to design. Now we have to come back to look at this. First, we will design the ground layer. Okay, this is the first and foremost layer. I will go to CST. I am going to design the ground layer. I told you already, the ground layer is the conducting layer. So I will take step 1, design of ground layer. So while designing the ground layer, what should I consider is its material. Material is copper annealed. I am preparing this document for my reference. Step 1 is design of ground layer. Its material is annealed copper. Okay. Modeling, and then click brick. Okay, and click anywhere in this rectangle or square, and then press escape. So I will type that also. Click modeling, then brick, click inside cube, then press escape button. Then you will be given this. Okay, this window will pop up where we need to name the layer and do all the parameter representations. This is my ground layer. So I am going to name it ground. This is the first layer. Okay, X minimum, X maximum. Have a look at this. Please pay close attention. I am going to define X min and X max. I've told you already. X values are the width values. Okay, Y values are length values. To design the ground layer, I should know the length value and the width value. But I know only the width and length of patch. Now have a look at this diagram. The length of ground is larger than length of patch. Similarly, the width of patch is lesser than ground layers width is greater than patch width. Ground layers length is greater than patch length. What will I do? I will check my patch value patch dimensions. Width is 17.92, length is 13.46. So my ground layer is going to be bigger than this one. So what would I do? I would choose width value a value larger than W of patch. It can be anything. So what is the width of patch? It is 17.92. I will do one thing. I will take a value 22, for example, okay, which is greater than the width of patch. Okay. Similarly, I will do for length also a value larger than L of patch. What is the length of patch? It is 13.46. So I will choose it like 18, which is greater than that one. It is not necessary to be an even number, but I prefer even number. You will understand why. Okay. You will understand the reason by yourself. So now I have the value for what is this? Ground layer. Just highlight it. For ground layer, I have the width and length. Now I know that this should be entered in x-axis and this should be entered in y-axis. Where do you enter this? In the CST software. Okay, I named it. Now I want to enter x value. What is my x value for a ground layer? It is 22. So what will I do? It is minimum and maximum. That is the requirement. So for minimum, I should divide the value by 2 and put minus 22 by 2 and plus 22 by 2. Because we are just separating it from the origin. From the origin, in negative region, half the value, and in positive region, half the value. Sir, why are you doing this? You can simply put minus 11. Yes, you are right. But the reason why I'm doing is, I want to know what value am I using. If I enter minus 11 here, then I may not understand the reason behind it. So when I put like this, I have the reference document where I mention clearly why I select 22, which is because I want to choose a value greater than W of the patch, which I already calculated from the website. Okay. I have entered the value for width. Similarly, I will do it for length also. I have 18. So this will be minus 18 by 2 and plus 18 by 2. Now, with respect to this figure, I have entered width value and length value. All right. Now, I am going to enter value center, and now I need to enter the thickness value. The thickness, this is z-axis. So y-axis, x-axis, the height is z-axis. So this height is normally see z-axis is for thickness value of the selected material. For the ground layer, I should define the thickness. So now I will decide it to be 0.035. This is a standard value according to the manufacturer. That is, after I design the antenna using this software, I will export the file and save it in my computer and send the same file to the hardware engineer. That hardware engineer will get the file from me and he will feed the file in the hardware manufacturing device like PCB prototyping machine or antenna prototyping machine. He'll be having a computer in which he will feed this file, the file that I exported. He will feed it onto it and he will do the real-time hardware fabrication. So during that time, the design engineer will use copper material. Like for ground layer, he will use copper. That is what we are going to mention. So the common copper thickness value that is used in PCB prototyping is 0.035. So I will use the value here. So initial value is 0 from the ground layer level. Please understand this is the first layer. So it is going to be 0 and the maximum value is 0.035. This is a standard value. I am telling this because whatever value you enter in the during the simulation process, you should justify it. You cannot put random values here. So please pay attention in this ground layer design. Look at the x and y values. Their minimum value will have minus values, but z value will never have minus value. Please keep in mind, z value the minimum value will never go to negative region. Okay, so this is the set of values that we should enter. After entering the value, this is going to be my first component. Okay, and I will choose the material type. It is not available here. So what will I do? I will choose it from the material library. Here I will type copper. When I type copper, I see two material types. I prefer annealed copper, and I press load. Before you click OK, make sure the value is correct. Then make a preview. This is going to be on the right side. I hope you can see this orange rectangle, orange colored rectangle. Now I hit OK. Now I can turn this. Okay, and see the first layer is ready. After doing this creation of ground layer, I check the same over here. This is my first component. It is ground. Okay. Suppose if I'm thinking about changing its values, either I can double click and go to define brick and change the values. But see, other things are frozen. Okay. I can right click on this and I can do edit material properties. Here I can edit it. Okay. Now the ground layer design is over. Now I'm going to design which layer? I'm going to design the substrate layer. From this figure, what do you see? You see the ground layer and the substrate layer both have same length and width. Okay. So here that is for thickness. So here I will enter the values for minimum and maximum. X min is equal to minus 22 by 2. X max equal to 22 by 2. Okay. We'll enter L value, which is Y minimum is equal to minus 18 by 2. Y max is equal to plus 18 by 2. This is for ground layer. Okay. Z axis, Z minimum is equal to 0. Z max is equal to 0.035 standard value. Okay. Like I already said, the material is copper annealed, so I don't have to do much. Finally, see, preview, and click OK. This is for your understanding. I am doing it. Now, step 1 is completed. Step 2 is here. Ground layer is completed. Now I am going to design the substrate layer. Design of substrate layer. Material is FR4. Okay. What we have selected initially. The material will be FR4. Again, I will go to just a moment. Please hold on. Again, I will go to modeling, brick, click somewhere and press escape. This is going to be my substrate layer. Okay. X minimum value from the figure you can see it is same as the ground layer. So what value did I use for ground layer? If I don't remember, I can select. Wait a minute. I know the value. It is here. See, I have the value of length and width of ground layer over here. See, X minimum is minus 22 by 2. I will use the same here. Minus 22 by 2. This is Y minimum is minus 18 by 2 and plus 18 by 2. Z minimum. Here, look at this. Initially, I have a ground layer. Its thickness is 0.035. From here, I hope you can see this cursor. From here to here, it is 0.035. So Z value of ground is minimum 0, maximum 0.035. Now, the Z minimum of substrate will be Z max of ground. I hope you can understand. Because we will start from the Z max of ground layer. The dielectric or substrate layer starts at the maximum Z point of ground layer. That is, have a look at this. That minimum is 0.035, which is the Z max of previous layer. Okay. Now I should define the thickness. What is the thickness of this layer? Also called the height of substrate. Thickness range is 1.6. So here I will use the thickness plus the Z minimum value. That is this value. Okay. 0.035. I will explain this. Look at this figure. For ground layer, Z minimum is 0, Z maximum is 0.035, which is a standard value. But for dielectric layer, Z minimum is Z max of ground, and that is 0.035. Okay. And this height is how much? 1.6. That's what we selected from the table. Okay. See, this one we selected initially from these three values are selected from table. Now, Z minimum of dielectric is 0.035. Z maximum is 1.6 is the thickness plus this 0.035 from the ground value. So when you represent Z max for any property, I mean any material, you should define the Z max from the ground level. For example, in this case, the height of dielectric, this point, look at the cursor, this point, height of this point is the Z max of dielectric. So from ground level, how long is it? This thickness plus material thickness, correct? So this thickness is 0.035, we know, and this thickness is 1.6 from the table that we initially select. Therefore, this value. I hope you understand. Now this is second component. So I click component 2. This material is not copper. So I will load from material library. This is FR4. FR4. When I type this, 3 materials are there. I will choose lossy. Okay. Then I click load. Now you can see the value is ready. Before clicking OK, I will check the preview. Another layer is ready on the previous layer. I'm going to enter the values in this document for my reference. So W and X min and X max values same as ground layer values. Z min is equal to Z max of previous layer. This is common to all layers. If I go for the design of next layer, then the Z min will be Z max of previous layer always. Okay, but the Z min of initial value of Z min is 0. So Z max of previous layer is equal to 0.035. Now Z max equal to 0.035. Or for your understanding, I will do one thing. I will change it like this is the what layer is this? This is step 2. This is design of substrate layer. We will make it for our understanding. I will make it Z min S, Z max S, Z min S plus 1.6. What is this 1.6? Thickness or height of substrate. Okay, from table. Okay, I hope you understand. So I will just simply enter this 0.035. I will write it again. Z max X is equal to what is Z min X? Z min S, what is this? 0.05, sorry, 035 plus 1.6. I may add these two and put like 1.635, but only for understanding I am doing this. Okay. Now this is component 2 and it is lossy. Preview is ready. Once I am ready, I am going to click OK. For understanding, I may take a screenshot of this. Paste it right here itself. Okay, this is for my understanding. Now the layer 2 is ready. Now I press OK. Now 2 layers are ready. Okay. The first layer is copper. The other layer is substrate. Is it clear so far, students?
Yes, sir.
Great. Don't worry, I will share this document at the end of the session because this document is for your reference only. At the end of the session, I will simply share this to you. I will give it to Professor Sir, or you can drop any one of your email ID in the chat box, chat session. I will keep you in the carbon copy, in CC also. You can make use of this document for your design and understanding purpose. Now we have designed two layers. Which are the layers? Ground and dielectric layers are ready. Now we will decide the third layer. Which one? Design, the patch layer, for which we have the length and width already. Actually, we are going to design the patch layer. Same process, go to, okay, I will type here. Step 3. Lady, I will share the necessary information. What should I do now? We are going to design the patch layer. So for patch layer, again go to step 3 is patch layer, for which we need W from the very first calculation. These are the patch dimensions. I will simply copy and put here for my understanding. This is from the website. Okay. Now x minimum is equal to, what is x minimum? 17.92. Okay, minus 17.92 by 2. And x max is equal to the same value in positive, 17.92 by 2. And y minimum is equal to 13.46 by 2. Say I left minus. And y max is 13.92 by 2. This is simple. Now z minimum is equal to z max s. What is z max s? The previous layers z max, maximum z. Okay. What is previous layer? For understanding, I put s, that means substrate.
So Y maximum value is 13.46 by 2, sir.
Correct. 13.46. Correct. Sorry, by mistake I put 13.92. This is how you make mistakes while designing your antenna. Thank you for notifying me. And Zmin is equal to Z max S, which is Z max of previous layer. Okay. Now Z max will be, so this layer is patch. So I will put a small p here. Z max p is equal to Z minimum p plus, do you understand this? Until this step, until this. Have you understood up to this point? The highlighted one?
Yes, sir.
Now, what I'm going to do is, I will define the thickness of this patch layer, which is same as the thickness of ground layer. What is the thickness of ground layer? Go to ground layer design, where it is over here. The thickness of ground layer is 0.035. So I will use the same value here also. Plus 0.035, which is equal to, from here I will enter the values. What is the Z max of previous layer? I will take from here. Z max of previous layer is, simply copy this, put here. So Z minimum is the Z max of previous layer. So this value, Z minimum value is this. Okay. So that value plus the 0.035. Already here is a 0.035. 0.035. Okay. Now we have all 6 values. X mean X max, Y mean Y max, Z mean Z max. Let us put it here. Again, go to brick, click, press escape. This is my what layer? Patch layer. So Z min is sorry, x min is minus 17.92 by 2, minus 17.92 by 2, and this is 17.92 by 2. Y min is how much? Minus 13.46. Y max is 13.46 by 2. What is that minimum value? It is 0.035 plus 1.6. Okay. And what is Z max? 0.035 plus 1.6 plus another 0.035. Okay. This is my third component in the design. And this is from here itself, I can select copper annealed. This is also copper annealed. Okay. I click preview. Now I have a patch like this. Okay. This is my patch. What would I do? I'm okay with the values. So I will take a screenshot of this. Will place it right here for my understanding. Okay. Is it clear so far now, students?
Yes, sir.
Fine. After checking the preview, I will hit OK. Now the layers are, you see, the bottom layer is yellow and the topmost is also yellow. I can change the material color also if I want. The substrate is kind of a mild pink, baby pink color. I can change its properties here, edit material property. From here, I can change the color. If I want to put it, make it red, I will make it red. Now it is turned red, okay? Or pink, whatever. Now I have changed its color. One, see the material thickness. Okay. Just scrolling up and down to change the view. Okay. Designed 3 layers. What are they? Ground, substrate, and patch. And so far we have designed up to 3 layers: ground layer, substrate layer, and patch layer. The fourth layer that we are, the fourth element that we add to the antenna is the feed. Okay. Step 4 is feed layer. So material is same as patch. Here it is annealed copper. Okay. Before we actually include the feed layer into this, actually the feed layer will come right here. I hope you can see. Here. I hope you can see the screen. So it's right here. Okay, over here it will come. For understanding, you can see this one. Okay, this is what the patch, feed is. For feed design, for this we need to calculate the feed size. That is the length and width of feed. Okay, I will explain. Okay, so for 3 layers complete, now we are going to design. I have already shown the details here. I will just copy it here. We will put it right here. In CST homepage, you may have to go to, this is the homepage, you see, the home. On menu strip, you select home, because earlier we were here, we were doing the brick design and all the parameters have been included. So far we have 3 different components: ground, substrate, and patch. Now go to home, and over there you see VBA macros. You go to calculate menu. Under this, calculate analytical line impedance. Now you can simply take a screenshot of this. I will just take a screenshot here for your reference. Okay. VBA macros, calculate line impedance. This is what you get. So go to the setup drop down menu. We are doing thin microstrip. So select it. So this is given for our understanding, height and epsilon. This sky blue color element is the substrate. Okay, please understand. We have to enter the substrate values, height and epsilon. What is the substrate parameters? I mean, what are the substrate parameters? Look at this. Substrate, we already calculated them from the table. Dielectric constant, epsilon is 4.6, and thickness, sometimes it is called height, it is 1.6. So now you come back here. Frequency, our antenna frequency is 5 gigahertz, let it be. The height value is, it is 1.6 from the table. Leave the width as it is, let it be. I will tell you why. Epsilon r is, this is epsilon r. See, epsilon r is, how much did we select? Epsilon r is 4.6. Right, 4.6. Okay. Here, if I click this calculate, look at this Z0 impedance value, it will be displayed. What is the value? It is 62. But the general value is static impedance value should not exceed 50 ohm. That is the standard value. And how may I change it? The height and epsilon r, they are fixed. I can only change the bit. How I change it? I will convert, I will change it to 3. Again, I will calculate. It's getting closer. So I should reduce it. 2.9. I get 50.81. This is okay. Close to 50. Now, this frequency is fixed. H also fixed. Epsilon also fixed. The only variable is W. So, you see the width of my feed. Where is my feed? My feed is here. The width of this feed is how much? 2.9. Okay. I will take a screenshot of this. Into this Word document. Okay, so that you can refer. Okay. Now what will I do? I will make a note of this 2.9. Okay, I will copy this. I click exit. That's all. Now here, width of feed from above W is equal to 2.9. That is X min is equal to minus 2.9 by 2. X max is equal to 2.9 by 2. Okay, now I have the X value and Y value is, Y minimum is 0. Okay, I will tell you why. And Y max is same as patch Y max. I think I'm right. Let me check that. In the feed design, see Y max is substrate value, not the substrate. Correct. Substrate. You see, same as substrate. I will tell you. Have a look at this. First, we have designed ground layer, followed by substrate layer, and then the patch layer. The patch is actually placed over dielectric, that is substrate. So whatever Y max value we used for patch, correct. Okay, I mentioned here as substrate of Y max, Y max of substrate. Okay, that is what mentioned here. Actually, the substrate width. This is correct. For patch design, I used substrate value. So here I use and this. Let me go and check my patch. Not right. It is not the patch one. It's actually the substrate value. Substrate Y max is taken here. So over here, same as substrate 18 by 2. Let me explain this. Have a look at this. Ground dielectric patch, everything is designed. We have the length and width of patch from the calculator, RF calculator in the website. And while designing the feed, we are just trying to mention the width of feed by using 50 ohm reference value that is mentioned here. Okay. using this analytical impedance calculation, we have come to a conclusion that the width will be 2.9. Okay. Then this width is 2.9 and length, actually we should calculate this length, which is same as that of the one we used for patch. Okay. I will show you. Once I enter the value, you will understand. Again, go to brick. This is the feed. X minimum is minus 2.9 by 2. It is plus 2.9 by 2. Y minimum is 0. Y maximum is 18 by 2. Okay. Z minimum and Z max. I will tell you Z minimum and Z max will be same as that of patch value. Okay. Look at this. For feed design, Z min and Z max value will be same as patch value. Because in this figure, you will be able to understand that the patch. Someone has turned the mic on. Can you please mute yourself? Good. Look at this. The ground layer, the dielectric, and after that we designed the patch. The patch and feed are on same platform. That is dielectric. Now, whatever Z values used for patch will be used for feed also. That is the logic here. Closed it by mistake. I will include. Go to brick. This is feed. X min is minus 2.9 by 2 from the calculated value. 0.9 by 2. Y minimum is 0. Y max is 18 by 2. I think I have mentioned it clearly. Z minimum is the. What is Z minimum of patch? It is in my document itself. I go to the patch section. What is the Z minimum of patch? This is my patch. It's 0.035. I mean, yes, 0.035 plus 1.6. Okay, look at this. 0.35 plus 1.6. This is Z max of patch. 0.035 plus 1.6 plus again 0.035. 0.035. This is component number 4. This is also annealed copper. I hit preview. This is how you get it. I hope you can see it. I will take a screenshot of it. Save it right here. Okay, now it's clear. So with this reference, you can easily understand. Now we have designed the feed layer also. But when you see, okay, now I press OK. This is how it looks like. Okay. I'm going to create, actually we have placed this feed layer on the patch. Now I'm going to merge feed and patch. Okay. Have a look at this. How do I do? First, I will select the feed. So if I click it, I will see only the feed layer. Then I go to Boolean. Then I press patch. Then I press enter. I will type it here. Merging feed and patch layers. Select feed from component under navigation tree. See, this is navigation tree. Look at this. This is navigation tree. Under this, from component, we select feed. Okay, that's what I said. Select feed from component under navigation tree. Click Boolean on. What is this? Modeling monostrip. Strip. Then click patch from component list on navigation tree, then press enter. After you do this, you will get the figure like this. So I will take a screenshot of this. And put here. So you will get figure like this. Now you are done with the actual physical antenna design. After this one, we need to simulate it. But since we have very less time now, I hope you understood how to make the actual physical antenna design. So after this we have some more steps like assigning ports and evaluating all the parameters. I will tell you how to do that. But with this short time, we are only able to design the physical structure of antenna. Now you have 4 different layers. Okay. After designing or even while designing, I can save just simply by pressing Ctrl S. I can save it wherever I want to. I can give the name. I will just name it like 5 gigahertz batch score November. Okay. Even I can save it on the desktop also. .cst file. I have just saved it. Okay. Now the antenna, physical antenna design is complete. If you have any doubt in this, please ask me.
Sir, am I audible?
Yeah, tell me.
So yeah, so I had a doubt. So while calculating the feed size, we used 50 ohms. So why is that particularly 50 ohms?
That 50 ohm is the standard value while designing it.
Okay.
It is a standard, like how we designed
For
ground
impedance
layer.
matching.
Yes, it
Okay.
is a standard value which is used for, as you said, for impedance matching. For which we need to discuss a few more. I don't want to confuse you right now
Sure, sure.
with
Okay.
impedance matching, because impedance matching has lots of important factors.
Hmm.
We have to deal with the actual impedance of the transmitter and receiver. Though we are
Hmm.
using the antenna for transmission and reception, anyways, it is going to communicate with the other circuit, which will also have transmitter and receiver.
Yes.
So in between, we need to consider the interference factors also. Lots of impedance matching factors. So I did not use the word impedance matching. So you can understand this while designing this particular feed. While calculating that, you have to stick to the value 50 ohm. You can keep it in mind, and maybe in further sessions we can elaborate that. But as you said, it is for impedance matching, and this value need not to be exactly 50. Like I said, under home, you go to this. Here's what we have calculated. Actually, how much did we calculate? This height is 1.6, 2.9. Epsilon r is 4.6. This is 50.81. Still, you can bring down. Like you may put it 2.85, 2.95. As such, you can bring it down close to 50. Okay. So it is a standard value like what we used in design of ground layer, like this. We have taken 0.035 for copper clad. Copper clad is the base element in PCB design, which is the first and foremost layer on which everything else is fabricated. So it has a common value. Or you can define it like, sir, no, sir, I want to design my antenna with a ground thickness of 0.045. Yes, go ahead, no problem. But the standard value is 0.035. Okay.
Yes.
Did I clear your doubt, Mr.
Yes.
Nitish?
Yes.
All right.
Yeah.
All right.
Got it.
Now I will do one thing. I will go through the complete document. So from here, then save the file. Okay. So we are done with the actual physical structures. See, sir, I have done this. And after this, we need to assign ports and other parameters are there. I will show you how. If you have any doubt, you can ask me.
Sir,
Yeah, tell me.
sir, could you comment on the importance of loss tangent?
Yeah, sure. Loss tangent is actually related with the type of substrate that we prefer. Loss tangent is a constant that will define the efficiency of the antenna. I have a representation here. Look at this. The formula is dielectric loss divided by stored energy. It is a pretty big calculation, but still I will summarize what is loss tangent. as the name says, it is the loss dissipated. See, we are dealing with electronic circuits which are energized, biased using DC power source or AC power source, whatever. So whenever power is involved, electric power is involved, there will be a loss of power, and that loss is dissipated in terms of in the form of heat. So in this antenna, show you here, we have two conducting materials separated by a dielectric. So this dielectric will face some heat development. So that is because of the loss. That depends on the type of material. For type of material, we have classifications here. See, based on this, the loss will vary. Look at this. It varies with the type of material. This loss tangent should be as low as possible. So if I am designing an antenna to work at 2 gigahertz, then I can go for any of these three or the fourth one also. It is my choice to select. But how do I select? How do I come to a conclusion that I'm going to use this type of substrate? It is decided by the loss tangent. So loss tangent is directly related with the efficiency of the antenna. Assume that you are designing the antenna for 5 gigahertz and your antenna is resonating at 3 gigahertz. That means the antenna is capable of transmitting and receiving the signals up to 3 gigahertz. That is its resonating frequency. So we can easily say that resonating frequency is the frequency at which antenna's efficiency is maximum. So at this point, the loss is as minimum as possible. That is the exact meaning, which means efficiency is high only when the loss is less. So that loss is determined by the type of material preferred. So that is what the importance of loss tangent. You cannot simply select any material to design an antenna. You have to consider this loss tangent. Though the application and frequency range is with us, it is our selection. Even for this 2 gigahertz, you can use this Rogers RT material also. See, that is also has a frequency range from 1 to 100. Did I clear your doubt?
Yes, sir. Thank you.
Fine. My pleasure. Okay, so far we have seen how to design 4 layers. 4 elements, 1, 2, 3, and feed, 4. Now we have just merged feed and patch layers. Now let us see how to determine, how to fix ports. For this, we go to, just a moment. Just give me a moment. So after this, I'm just going to change the view. Okay, I've just zoomed it. So I'll be placing the port right here. Hope you can see the cursor. Go to pick phase. Double click here. Once I make double click over here, I see some dotted lines. I repeat the step. Once I'm done with all 4 element design, I go to modeling and then I choose pick and then pick phase. I will type it here. Save the file. Go to modeling. Before that, zoom in the phase of feed. Okay. Go to modeling. Select pick and then face. This time, what would I do? Modeling. Click face. I will take a screenshot of this. Right here for your reference. Okay. Modeling. Pick face. I have already done this. Double click on the face of. Double click on the face of feed to see dotted. Okay. And then go to macros, VBA macros. Then go to solver, where you'll be seeing ports. Okay, and calculate port extension coefficient. I will just take a screenshot of this also. Macros. To this, go to solver ports. It's not coming, so I will simply do one thing. I will type the entire thing here. The screenshot, I'm not able to capture it. I will do one thing. Then go to home, VBA, macros. Okay. Solver, ports, calculate port extension coefficient. Okay. Port VBA macros, solver, port extension coefficient. Okay, here you see these values are fixed. So the epsilon r is 4.6 that we selected. I will show you. It's here. How much we select? Epsilon r that we selected is 4.6. Okay. You just click calculate. This is for our reference. So after clicking calculate, or even without that, you see this value is selected already. We only entered this value before starting the construction. So construct pole from pick face. Check epsilon r value. Click on construct port from picket face. Construct port from picket face. Click this. Actually, I did not select it. We'll do one thing. Pick face. And then home, VBA macros, solver, port, fix. Give me a moment. Actually, I should do it here. Modeling, pick face. Okay. pick face and go to home, solver. So once you're done with this, it should display something. Just a moment. I'm facing a technical glitch here. I will tell you what to do. Okay, this is how it comes. Actually, I'm having a glitch. After we complete this step, what is this? Click on construct port from picked face. What happens is actually you get this kind of, you see, a setup like this, after which we need to run the simulation. So once we are done with this, we can save the file. Here we can export it. So this is all about the design of antenna. Then what we do, we will just simply export. You can see 2D files. This is a limited version, so we are not having the ability to export it. So you see 2D files under this Gerber single layer is what we do. Once we click this, and a dialog box will pop up where you can rename the file and save it on your computer, which will be used by the hardware engineer to design hardware antenna. Okay, is it clear? So from this page, so once you're done with the actual design like this, after merging the feed and patch, you go to home, macros, solver, ports, calculate port extension, check epsilon value, click on construct. Okay. With this, the steps are over. Then run the simulation. That's all. This is all about it. Let me tell you all about antenna design. So after this port assignment, we have to simulate the antenna. We have to check its the antenna performance. Check the antenna performance, whether it is coming into our requirements boundary. And there are some more restrictions, constraints which we need to follow. It will take some more time. So this is only a basic class in which you have understood the antenna design. So I will summarize the process shortly. We have 3 layers. Ground layer is a conductor, annealed copper. The other second layer is a substrate layer, which is depending upon loss tangent and frequency selection. Patch is also a conductor, annealed copper layer, where the feed, it is also copper, which is placed and merged. We call it merging. And that was done using the function Boolean here. Okay, using Boolean function, we merged it. And finally, we have fixed port onto this over here. After introducing the port, we have to run the simulation and check for results, which we may discuss in the future classes when time permits. And that's it from my side. Thank you, Shweta, and thank you all the participants.